Hello everyone, I am Sharon from the Department of Computer Science and Engineering, Hindustan College of Engineering and Technology, Coimbatore. In this video, we are going to explore a very important and fundamental concept in digital electronics, the half adder and the full adder. This topic is part of the course 22CS3203 Digital Principles and Computer Organization. Have you ever wondered how a calculator performs addition? Or how your computer processes numbers behind the scenes? It all begins with something very simple, a digital circuit known as an adder. These circuits are used to add binary numbers, the language of computers. In this session, we will take a closer look at two types of adders, the half adder and the full adder. Let's get started with the half adder. So what exactly is a half adder? A half adder is a combinational logic circuit. That means it does not store any values. It just processes inputs to produce an output. Its main job is to perform addition of two single bit binary numbers. It has two inputs, usually labeled A and B, and it produces two outputs, sum denoted by S and carry denoted by C. The sum is the least significant bit and the carry is the most significant bit. These adders are widely used in the arithmetic and logic unit of computers for basic arithmetic operations. Now let's take a look at the block diagram of a half adder. Here we can see that the circuit takes in two inputs, A and B. These inputs go into the half adder block, which then produces two outputs, the sum S and the carry C. Let's understand how the half adder works by looking at its truth table. Take the second row where A equal to 0 and B equal to 1. 0 plus 1 equals 1, so the sum is 1 and the carry is 0. Now take the fourth row where A equal to 1 and B equal to 1. 1 plus 1 equals 2, which is 1 0 in binary, so the sum becomes 0 and the carry becomes 1. Similarly, when only one input is 1, the sum is 1 and the carry is 0. When both inputs are 1, we get a carry of 1 and the sum is 0. Now let's simplify the half adder circuit using K-map. Since we are dealing with two input variables, A and B, we use a 2 by 2 K-map. We know that the number of cells in a K-map is 2 power n, where n is number of variables. So for n equal to 2, we have 2 power 2, which is equal to 4 cells in total. Here, A represents rows and B represents columns. First, for the sum S output, we need to mark the cells corresponding to input combinations where the sum is 1. That happens when only one input is high. A is 0 and B is 1, or A is 1 and B is 0. So we place 1s at these positions. The simplified expression we get is S is equal to A bar B plus A B bar, which is equivalent to A XOR B. Next, for the carry C output, we mark the cells where both A and B are 1. This is the only case where carry is 1. So we place a 1 there and the simplified expression is C equal to AB. Now let's quickly look at the characteristic equations of a half adder. The sum is given by A B bar plus A bar B. So according to binary addition rules, this is the logic of an XOR gate. So we can write S equal to A XOR B. So the carry C is 1 only when both A and B are 1. So C equal to A dot B, which is an AND operation. So these two equations define the logic of the half adder. This is the logic circuit of a half adder where the XOR gate gives a sum and the AND gate gives the carry. Now let's move on to the full adder. A full adder is a combinational logic circuit with more capability. It adds 3 single bit binary numbers, 2 inputs A and B and an extra input called Cin, which stands for carry in from the previous addition stage. It produces two outputs, the sum S and the carry out C out, which can be passed on to the next stage in multi-bit addition. Here is the block diagram of a full adder. As you can see, the three inputs A, B and Cin go into the full adder circuit. The outputs are sum and carry out. This carry out is then typically fed into the next stage if you are doing multi-bit binary addition. Now let's understand the full adder truth table with a couple of examples. Take the first row where A equal to 0, B equal to 0, Cn equal to 1. So here 0 plus 0 plus 1 equals 1. So the sum is 1 and there is no carry. So C out is equal to 0. Now let's look at the 7th row. A is 1, B is 1 and Cn is 0. So 1 plus 1 plus 0 equals 2, which in binary is 1 0. So the sum is 0 and the carry out is 1. Similarly, for each combination, the sum is 1 when the number of ones in the inputs is odd. The carry out is 1 when there are 2 or more ones. Now let's simplify the full adder circuit using K-map. Since we are dealing with 3 input variables A, B and C in, we use a 2 by 4 K-map. So we already know that the number of cells in a K-map is 2 power n, where n is the number of variables. So for n equal to 3, we have 2 power 3 which is equal to 8 cells in total. So here A represents rows and BC in represents the columns. So for the sum as output, we mark the cells where the output sum is 1. In this case, we can't form any groups with diagonal ones, even though they are adjacent, so each one is treated as a single group. So the simplified expression is S is equal to A bar B bar C in plus A bar B C in bar plus A B bar C in bar plus A B C in, which is equivalent to S is equal to A XOR B XOR C in. Next, for the carry C out output, we mark the cells where the output carry is 1. Now let's group the ones in the K-map. So we are having group 1 with minterm 6 and minterm 7. So here common variable is A equal to 1 and B equal to 1. So this group gives us AB. So we will be having another group 2 with minterm 5 and minterm 7. So here common variable is A equal to 1 and Cn equal to 1, which gives us ACn. So we will have another group also, group 3. So having minterm 3 and minterm 7. So here common variable is B equal to 1 and Cn equal to 1, and which gives us BCn. So the simplified expression is C out is equal to AB plus ACn plus BCn. Now let's quickly look at the characteristic equations of a full adder. The sum S is given by S equal to A bar B bar C in plus A bar B C in bar plus A B bar C in bar plus A B C in. So according to binary addition rules, this is equivalent to the XOR of all 3 inputs. So we can write S is equal to A XOR B XOR C in. So the carry out C out is 1 when any 2 or all 3 inputs are 1. So the carry equation becomes C is equal to AB plus ACn plus BCn. So these two equations define the logic of the full adder. This is the logic diagram of a full adder. It has 3 inputs A, B and Cn. For the sum as, we use a 3 input XOR gate. For the carry C out, we use 3 AND gates and 1 OR gate. Now let's quickly compare half adder and full adder. A half adder has only 2 inputs. It can't handle carry in values. So it's great for the first stage of addition. But for adding multiple bits, we need to carry over values from the previous additions. That's where full adders shine. They have 3 inputs including carry in, so they are suitable for multi-bit binary addition. So in real-world digital system, both types work together to perform arithmetic operations efficiently. To wrap things up, adders, whether half or full, are core components in digital electronics. They are present in calculators, CPUs, and almost every digital device that performs arithmetic. Without them, your devices wouldn't be able to perform even basic addition. That brings us to the end of this session. Thank you.